Ladies and gentlemen, now next off， 下个阶段呢比较特别了，这是2个人做同一个报告。Okay, we have 2 for 1 presentation, 2 persons for 1 presentation. 这2位分别是 from NI, Nicholas Keel, and from Ansys, this would be Kishor Ramaswamy. 2位分别呢是 Offering Manager of Automotive, ADAS, AD Validation, 还有呢另外一位则是 Application Engineering Manager, Optics and Autonomy. 好的，接下来呢，我们就把现场呢要透过预录的影片交给 Nicholas and Kishor.
Hi, welcome to the NI webinar about solving the challenges of camera HIL for ADAS and autonomous driving. I'm Nicholas Keel, Offering Manager at NI for ADAS and Autonomous Vehicle Test, and joining me is Kishor from Ansys.
Hi, this is Kishor Ramaswamy, Manager of Application Engineering with Ansys. I cover our optical simulation portfolio as well as our Ansys Autonomy simulation platform.
Great, thanks Kishor. So today we're going to talk about some industry challenges about how we're going to get ADAS and autonomous vehicles to market, and then we're going to talk about some ways to improve our test workflow and some best practices for getting more test coverage with less cost and less time. So let's first start with the challenges. So right now there's still a lot of regulatory uncertainty as regulators are trying to provide us with as much freedom to innovate as fast as we can. But that leaves us with little guidance about how we need to test, how much testing needs to get done in the scenarios we need to cover, which creates a massive volume of testing that we're currently needing to do as best we can and ensure as best we can that the vehicles are safe before we put them on the road. And combining that with the additional complexity of systems, we're no longer testing individual components as part of an ADAS function, but testing interconnected components as part of larger systems that contribute to more sophisticated functionality. Incorporating new technologies such as machine learning, which makes things much more difficult as we don't always know how machine learning algorithms are going to respond. We need to be extra diligent in making sure we cover those test scenarios with increased coverage and scrutiny. So to do all of this, the natural tendency is that we want to move more and more of our testing into simulation. We want to get more testing, more miles, more scenarios for less cost and less time. So moving into simulation is a natural progression that we want to incorporate. We want to move our testing as far left as we possibly can. The things that are keeping us from being able to do that is an inherent trust in simulation. We need to ensure that we believe that the fidelity of the simulation accurately represents the real world so that the tests that we run can reliably be related to real world scenarios. For that to happen, simulation fidelity needs to continue to improve. And here we're going to talk about how we've made steps to improve that fidelity and how the NI and Ansys tools are being used together to make simulation more reliable and help us get more miles for less time. So to make all of that happen, in order for us to truly trust simulation, first of all, we need high fidelity across the board. We need high fidelity environments, we need high fidelity sensors to interact with those environments, and we need reliable vehicle dynamics to make sure that the scenarios that we're covering can really be qualified and tested in accordance with a real world scenario. And then we need to take all of those scenarios and we need to run them in massive parallel environments, whether that be a cloud-based infrastructure or an on-prem IT infrastructure. We need to run everything in parallel so we can cover as many miles in as short a time as we possibly can. And to that end, NI has been making significant investments to improve our simulation capability. So we recently acquired Monodrive to include high-fidelity environmental simulation into our platform for real-time hardware-in-the-loop testing. So Monodrive is a Unreal-based engine that's real-time capable, very well complements hardware-in-the-loop test systems, incorporates sensor simulation, and we can also take real data that we've recorded in test tracks and test runs in our fleet. We can convert that into simulation data, which can then be used to run simulation and to create permutations of specific scenarios for greater test coverage. And then obviously all of that can be deployed on a cloud infrastructure for massive parallel scaling. So now I'm going to hand it over to Kishor to tell us a little bit more about Ansys and the NI partnership.
Thanks, Nick, for that introduction. So a few words on Ansys. Ansys is the world leader in simulation software with 40, 50-year plus experience around our full physics portfolio of mechanical, electromagnetics, and fluids, working across a number of different industries. But more recently, we've put a considerable amount of investment into our autonomous vehicle offering with acquisitions in high-fidelity sensor simulation, in model-based systems engineering, and in safety design and development. And this allows us to really offer a unique portfolio to the industry inspired by the Safety First white paper on safety by design and safety by validation. We can look at, first the safety by design, looking at model-based systems engineering for addressing functional safety needs, ISO 26262, SOTIF, or safety of intended functionality, as well as cybersecurity, and also the general sensor design, making sure that is meeting the requirements from a safety perspective. But then looking at the safety by validation, which is really the focus of what we're talking about today, using that sensor simulation to create high-fidelity physics-based sensor models that can feed into open and closed-loop SIL and HIL validation systems. And this really allows us to scale, allows us to reduce the time to market and the cost, and improve the overall safety of these autonomous systems and ADAS features. So combining NI and Ansys together, really the goal is to combine this into a continuum safety-driven design and validation platform. We rely on a few things: an open ecosystem, software-centric simulation platform, reusing the same tool chains throughout the entire process, from open-loop replay all the way through to closed-loop SIL and HIL, and relying on high-fidelity physics-based sensor modeling, physics-based environment modeling to really produce synthetic data earlier in the process and ultimately reducing the amount of field testing that's required. So let's look at one concrete example. Here we're looking at testing of intelligent headlamp systems. So this is traditionally done through physical testing, night drives, which has a number of issues. One is that these environments are highly unreproducible. Two is that it's very costly and time-consuming to do these tests physically. And also, frankly, for the drivers, there's safety concerns in testing these features at night. So we want to push this more to the left. We want to leverage simulation, in particular HIL testing, to reduce the amount of physical testing that needs to take place. This has a number of challenges, especially for nighttime. We really need to make sure that the simulation that's being produced, the synthetic data that we're producing, is representing the artifacts and the phenomenon that the real camera system is experiencing in the real world. And in particular for nighttime testing, one of the things that's critical is the illumination. And you can see that on the screen here, the very bright headlamp spot compared to the dark contrast around it. This is primarily what these perception systems rely on at night for performing detections. So we need to make sure that we're accurately simulating the illumination from these headlamp systems, as well as how that illumination is processed, the conversion from photons all the way through to electrons, and make sure that we're maintaining all of the artifacts that can be introduced through that entire process. And of course, from a light interaction perspective, we need to make sure the materials within the environment are accurate so that we're getting proper reflections off of the road or off different signs coming back into the camera system. So all of this really requires high-fidelity sensor modeling, physics-based sensor modeling, in order to replicate what's happening in the real world so that we can use HIL testing, simulation and HIL testing, to push everything to the left. So looking more concretely at how the Ansys and NI technologies are being combined together, we have a couple of things that you can see on the right. And all of this is feeding into the NI stack. So we have first the safety analysis, so doing that model-based systems engineering inside of Medini and feeding that into the safety requirements. Then looking at the embedded software and using our auto code generator, which is certified for ISO 26262, to generate software models that can be used as part of the HIL testing. And finally, looking at the high-fidelity physics-based sensor models from the Ansys software combined with the scenario generation, environment generation of the monodrive tools to allow for virtual testing through simulation. So now I'll pass it back to Nick to walk us through what the HIL system looks like.
Thanks, Kishor. So when we're talking about hardware-in-the-loop simulation, we've got a few different options that we can pick from. So we can do object list for sensor fusion algorithms, for planning and control algorithms. We can provide object lists that represent the outputs of sensors. Or we can incorporate sensors inside the HIL system and do over-the-air stimulation using something like NI's VRTS product. For many cases, however, we'll want to do high fidelity sensor simulation like Kishor was mentioning and combine that with high bandwidth digital injection. So that's kind of that middle path. We're going to inject raw data from real sensor or real high fidelity sensors into either a sensor ECU or a fusion ECU depending on the topology. So what that looks like is we use the Ansys software to do the high fidelity sensor simulation. We input that at a high data rate into our FPGA-based high-speed serial instruments over the HDMI port, and then we use the PXI system to connect to the camera interfaces that are connected to our ECU through either GMSL or FPD link or typical standard in-vehicle camera interfaces. And what this allows us to do is it allows us to encode and decode the video signals on the input and also add errors into the stream to actually exercise and thoroughly test that ECU perception algorithm. So what does that actually look like in practice? We take the Ansys software, the Ansys simulation software, we put that out of the GPU through the HDMI port into the NI HSDIO or high-speed digital board where we do the decoding on it, pass that across the backplane into our camera injection module that is also equipped with an FPGA, connect that through FPD link or GMSL to the ECU to run our tests. All right, so that's a high-level block diagram of what a system might look like. Let's take a look at our demo for this particular application. So what we have here is we have a high-performance computer here running a GPU running the Ansys simulation software. Out of the back of this, we've got an HDMI port that's being connected to our PXI system to our HDMI input port. Let's take a quick look at what's inside the PXI. So on the PXI system, we've got our embedded controller, which is running a real-time operating system to handle all of the I/O. We've got our HDMI input, which it gets handled into the FPGA board through an SFP plus connector. That video signal gets connected along the PXI backplane, which runs a high-speed timing and synchronization clock into our FPGA-enabled camera interface module that either has interfaces for GMSL or FPD link. In this case, what we're doing is we're doing a loopback, so that enables us to view both the data that gets put into the RT system from the simulation software, as well as the manipulated data where we've injected some errors and done some video processing to replicate what would actually go into an ECU. And then the system can also be equipped with peripheral interfaces for embedded networks like CAN, LIN, and FlexRay, as well as standard Ethernet interfaces and Automotive Ethernet interfaces. So this is what the hardware looks like. Let's take a look at the demo. So now what we have here is we've got a tile on the left that is what's going on in the input of our HDMI interface. So this is what's coming out of the Ansys simulation software. And on the right, what we have is the output of our camera interface module. So we're getting the data from the simulation software, we're decoding that raw data, and then we're putting that into our error injection module that can also talk to automotive cameras and ECUs. And we're able to visualize both simultaneously. And then below that, we're able to do some image analysis, putting it into a histogram so we can compare what's on the input and what's on the output of our hardware-in-the-loop system. And then we're able to create a test panel, which includes a variety of different features. We've included a couple of examples of what we might want to do to inject errors and to create tests. So what you can see here is we're dropping frames. So here, using the FPGA on the camera card, we're getting the full frame rate of the video, but we're able to test the ECU and see how the ECU responds by dropping independent frames. And then we track the number of frames that were input and the number of frames that we outputted, just to keep track and to be able to automate all of these tests. And all of these things come with APIs, so you'd be able to run this in an automated environment. We're showing you here interacting with the display and adding these faults, but we can certainly do this in the cloud or on-prem using an automated framework. Okay, so we've dropped some frames, we've seen our ECU response, we've tracked that, we've logged that, we know what's going on. Now we're going to start to manipulate the individual pixels on the image. So here we're we're picking which pixels we want to be black. We can pick individual pixels if we want. We're just doing a large collection of pixels. And we're also able to change the color of those faulted pixels so that we can very easily track them, again, with the intention of seeing how the ECU responds. All right, so we've manipulated individual pixels. Now we're going to take a look at manipulating the whole image. We're changing the brightness of that image, again, to see how the perception algorithm works in a whiteout condition or in a scenario where the lighting is poor. If we can black it out or white it out, we can see how our perception algorithm responds. And then the last piece is adding Gaussian noise. So here, again, at what point does our perception algorithm stop detecting objects? We're able to add Gaussian noise here to see when the confidence drops, where we no longer are able to track what's in the video. And these are just some examples of the types of things you can do in a real-time environment, incorporating image manipulation. And then, while we're doing all of this, we're recording and tracking the histogram, so the data of the images. We're able to track how they're different. So we're very easily able to replicate this in the future. We track all of the different parameters of those images, so that way we can run it in an automated environment. And now we blow up and zoom in on this image, and we can get a whole new series of characteristics. I'm going to have Kishor tell us a bit more about what's going on here.
Perfect. Thanks, Nick. So what we're looking at here, as Nick mentioned, is the output from the Ansys simulation. But if we take a step back, what's really happening is we're simulating the world and the light in the world. And all that light, which is a full spectral simulation, so we have all the wavelengths of the light, is being processed through the camera system. When that light goes through the optics and into the imager, it becomes a digital signal. So we've gone through and gone through the color filter array and created a digital signal. And really what we're seeing is that demosaic signal, so the decoded signal. So we can change that decoding structure from before looking at more of an RGB decoding, here looking at more of a black and white decoding. So this is typical of an RCCC color filter, one of the standard color filters that is used in the automotive industry, whereas the previous one is more of an RGGB color filter. So we can really look at the decoding of that digital signal and what that gives us. And here, now what we can also do is look at the raw signal. So the raw digital value, the voltage essentially that's being transmitted from the simulation before any post-processing takes place is also available, and that's what we're visualizing on the screen here. And this is most commonly used when we actually need that raw digital signal to be sent to the ECU. Many ECUs rely on raw data to perform their perception algorithm, and they don't want any post-processing to take place. So we have access to that raw data, and we don't need to decode it. We can simply pass that raw data into the ECU. Back to you, Nick.
All right, thanks, Kishor. So we've seen a demo, we've seen how the physical system is set up, and we've taken a look at a use case where we're testing a camera ECU. This can certainly be expanded to incorporate more robust environmental scenarios and variables, as well as vehicle dynamics, to test both additional sensors as well as sensor fusion algorithms. So we're really just building on top of what we've shown you here today for more complex systems and hardware-in-the-loop testing of systems of systems. And the HIL testing infrastructure is a key part of the ADAS and AD software V&V chain. If you've seen some of the other webinars that we've done, we've done webinars about the data recording systems where we can record a lot of data and acquire that and inject it into an IT infrastructure where we can tag it and manipulate it and add it. And we can also convert that into simulation for running closed loop, hardware in the loop, model in the loop, software in the loop, and connect that to an ECU. So between NI and Ansys, we're working on an end-to-end unified tool chain for testing AV compute stacks across the board. And if you'd like to learn a bit more, we've got additional content and additional material to learn more about both what NI is doing in ADAS V&V for hardware-in-the-loop testing as well as data recording, and how NI and Ansys are working together to accelerate time to market for ADAS and autonomous vehicles. And now, we'll answer some questions.
Okay. Thank you to Nick and Kishor. Nick is from NI and Kishor is from Ansys. Simulation and demo. Solving the challenges of camera HIL for ADAS and autonomous driving.